And we have part 7, number 21. Bead of mass M slides without friction on the inside of a rotating conical surface whose half angle is alpha. The cone rotates about its symmetry axis with constant angular velocity, capital omega. Gravity acts downward. Determine the generalized coordinates, kinetic energy, the potential energy, Lagrangian, the equations of motion, the equilibrium positions, the conditions for stable equilibrium, the frequencies of small oscillations about the equilibrium, and all conserved quantities. Limiting cases, capital omega approaches 0, alpha approaches 0, and alpha approaches pi over 2. So this is a comprehensive problem here. So part A here, use generalized coordinate S, the distance along the cone from the apex, okay, and let phi be the bond's coordinate around the cone relative to the cone. The cone is going to rotates with angular speed, capital omega. So the inertial azimuthal angle is here, capital phi equals lowercase phi plus capital omega t. So our radius from axis is rho equals s sine alpha, and our height is z equals s cosine alpha. For the kinetic energy, T equals 1/2 m times the quantity S dot squared plus rho squared, capital Phi dot squared. And for our T equals 1/2 m bracket S dot squared plus S squared sine squared alpha times the quantity here, times quantity phi dot, lowercase phi dot plus capital omega squared, close bracket. Part C, the potential energy, V equals mgs cosine alpha. And for part D, the Lagrangian L equals 1/2 m bracket S dot squared plus S squared alpha, lowercase phi dot plus capital omega, that quantity squared, close bracket, minus mgs cosine alpha. Okay, now picking up with this, sorry about that, just waiting for this. Okay. So since lowercase phi is cyclic, p sub phi equals the partial derivative of L with respect to lowercase phi dot, and that equals ms squared sine squared alpha, this quantity, lowercase phi dot plus capital omega, that is conserved. So the Euler-Lagrange equation for DDS, for S, ddt, bracket ms dot minus bracket ms sine squared alpha, parentheses, lowercase phi dot plus capital omega squared minus mg cosine alpha, close parentheses, equals 0. And S double dot equals S times S squared alpha, parentheses, lowercase phi dot plus capital omega squared minus g cosine alpha. And our equation for phi, or phi, for lowercase phi, d dt, ms squared sine squared alpha, this quantity, lowercase phi dot plus capital omega, bracket, close bracket, equals 0. So our equilibrium with S equals S naught, S dot equals 0, and constant here, phi, lowercase phi dot, requires S naught sine squared alpha, phi, lowercase phi dot plus omega squared. Okay, and that equals this, sorry about the focus here. And that equals this g cosine alpha. So S naught equals g cosine alpha divided by S squared alpha, quantity lowercase phi dot plus omega, that quantity squared. And for equilibrium stationary relative to the cone, that phi dot equals 0. And S naught equals G cosine alpha over capital omega squared sine squared alpha. So small radial oscillations are easiest using the effective potential with P sub lowercase phi. So U sub EFF of S equals mgs cosine alpha plus P sub lowercase phi squared over 2ms squared sine squared alpha. Then du sub EFF ds equals mg cosine alpha minus P sub lowercase phi squared over ms cubed sine squared alpha. So our equilibrium mg cosine alpha equals P sub lowercase phi squared over ms naught cubed sine squared alpha. And our second derivative here, u sub EFF double prime of s equals 3 P sub lowercase phi squared over ms to the fourth sine squared alpha. So at equilibrium, u sub EFF double prime of s naught, that equals 3mg cosine alpha over s naught. So omega sub s squared equals 1 over m u sub EFF double prime of s naught. And that's going to equal 3g cosine alpha over s naught. Okay, so building on that, omega sub s equals square root of 3g cosine alpha over s naught. And our conserved quantities, p sub lowercase phi, that equals a constant. And because the Lagrangian has no explicit time dependence in the rotating coordinate formulation, E sub ROT equals constant. So our limiting cases here, capital omega approaches 0, no centrifugal support if the bead is stationary relative to the cone. Alpha approaches 0, the cone becomes narrow. Sine of alpha approaches 0, so the required equilibrium distance tends to infinity. And alpha approaches pi over 2, the cone becomes nearly horizontal. Cosine of alpha approaches 0, so the gravity along the surface, it vanishes. Okay, so that is all for number 21 and part 7, and that's all for this practice final exam. Thank you very much and have a great day.